All right, I wanted to go back to this slide for a couple of minutes just to show you something on there. I wanted to have this unit circle in to show you a little bit more about the coterminal angles. Just to give you another kind of heads up on what they are. Yesterday we looked at 3 pi over 4. I want to show you what 3 pi over 4 is. It's right here on your unit circle. If you have your unit circle, you could probably see it on there where 3 pi over 4 is. 3 pi over 4 would be this angle in standard position. You'd start here, and you'd end up right here. So go this direction. That would be 3 pi over 4. Now yesterday we added 8 pi over 4. Do you remember why I chose 8 pi over 4? Because it equaled 2 pi, which is one circle, and it had a common denominator of 4 so that I could add my fractions. So that gave me 11 pi over 4. Now I want to show you where that would be. Now if you start right here, this right to go here would be 1/4. It would stop right there, 1/4. If I kept going, that would be 2/4, 3/4, and that would be 1 whole pi right there. That's 180 degrees, which equals pi. Then we would keep going, that would be 5/4, 6/4, 7/4, you can see right down here, and then 8/4 would be 2 whole pi's. 8 over 4 we said was 2 pi. Same thing as 2 pi. So if I kept going, that would be 9/4, because I just keep adding another fourth every time. 9/4, this would be 10/4, and I would stop right back where I had my 3/4 at. That would also be 11/4, 11 pi over 4. That's the exact same angle as 3 pi over 4, except it went around one extra time. So they're angles that are in the same position, but one has one extra rotation than the other one. So they would look the same, but you've got to be careful to make sure you put your arrows in to show that if I just go straight to here, it's 3/4. If I go all the way around once and then go straight to there, it's actually 11 pi over 4. So that was just a little bit of yesterday just added to it. So let's get to today's stuff, which is converting from degrees to radians. That's where we're going to start. We're going to go from degrees to radians. So here's our conversion factor. The best conversion factor we have is that 180 degrees equals pi. Pi radians. 3.14 radians is equaling 180 degrees. That's the one thing you had to remember from Friday, is that 180 equals pi. So if I wanted to find out what 135 degrees was, right here, I could set up a proportion. I could put x over pi. How many radians out of pi radians would 135 out of 180 be? And I could set up a proportion for it. Now that's the long way to do it. I'm going to show you what the shortcut is by what I'm going to do when I solve this. When I solve this, I'm going to get 180 times x, and I'm going to get 135 times pi. And then I'm going to divide by 180. And really what I did here, and I'm going to break it into two pieces just to show you. You normally wouldn't have to do this, but these would cancel out. And I'm going to break this into 135 times pi over 180. Because I've got I'm multiplying 135 times pi and I'm dividing it by 180. This right here is your conversion little factor that we use. We basically want to see how many 135s can go into 180, or can I reduce that? And the answer is yes on this one. You could actually divide them both by 45 and get 3/4. So this answer would be 3 pi over 4 radians. If you had your unit circles out, if you looked at them, and you went to 3 pi over 4, let me go back a couple of slides to show you again. 3 pi over 4 was 135 degrees. So 3 pi over 4 converts to 135 in degrees. Those two are the same amount. So let's apply that to 540. Let's take 540 and multiply it by pi and divide it by 180. Because that's how I convert. I want to see what I get, what I reduce this fraction. I want to make it into radians, which are smaller, so I'm going to put the 180 on the bottom. Now, could I reduce these two right here, 540 and 180? I could actually divide them by 180. If I divide by 180, I'm going to get a 1 on the bottom. I'm going to get a 3 on the top. So what's my actual answer for 540 degrees? 3 pi. What is 3 pi on my unit circle? Good. 1 circle and a half. Right here is 1 pi. Back to here is 2 pi's. Back to here is another pi, 3 pi. So it would be 1 circle and a half would be 3 pi. Negative 270, we'll take negative 270, we'll multiply it by pi and divide it by 180. So that's how I'm going to convert from my degrees to my radians. Could I reduce these two? By what? 30 is the one that would work. If there's a bigger one, 90 would be your best. So 270 divided by 90 is 3. 180 divided by 90 is 2. So you're actually going to get negative 3 pi over 2 radians. Where would that angle be on my circle? Or if I had my x and y axis, where would negative 3 pi over 2 be? Here's negative a half, right? Negative a half a pi. Here's negative 1 pi. Here's negative 1.5 pi's would be right here. So this angle, this backwards angle would be negative 3 pi over 2. This angle right there. If I went the other direction, I'd be down at the bottom. That'd be positive 3 pi over 2. So that's converting from degrees to radians. You're going to multiply it by the pi over 180. That will get you your radian measure. What about if we want to go the other direction? What if I have the radians and I want to find out what it was in degrees? So that's my next slide. Radians to degrees. Let's take a look at that one next. So again, the key point is pi radians equals 180. This one's even easier. If you have a pi in your problem, just plug in 180. Take out pi, put in 180 in its place. Because these two are equal to each other. You could always substitute them whenever you want to. Or you could use a proportion, which I'm going to show you as well. That might come in handy when you don't have a pi like this one or like this one. You don't have a pi in there. So let's look at 3 pi over 4 radians. We know the answer from our last slide. Hopefully you saw it. You look at your notes. You have your last slide. Do you remember what 3 pi over 4 radians was? It was 135 degrees, right? Let's see how we get to that 135 degrees. Let me just move this up. Okay, so I'm going to take out the pi and I'm going to put in 180. And I'm going to divide it by 4 there. 3 times 180 is 540. And then divided by 4, that's how I get 135 degrees. So 3 pi over 4 equals 135 degrees. Take out the pi, put in the 180 in its place. Okay, so just take out pi, stick 180 in its place, you'll have a conversion. Because pi means 180 degrees. So when they're saying 3 times pi, really they're saying 3 times 180 and then divided by 4. So this bottom one here, you're going to take 9 times it by 180 and divide it by 2, because you can take out the pi and you can put in 180 in its place. What do you think about this one? Should I multiply 9 times 180 and divide by 2, or is there an easier way to maybe do this? What was that? Could I reduce the 180 and the 2? I could. How many times does 2 go into 180? 90, so make that a 1 and a 90. What's 9 times 90? 810 degrees, yes, 810 degrees. That would be the quickest way. Now, if you did 9 times 180, you get like 1620, and then you would divide by 2, you'd still get 810. So either way, you get 810 there. What about when you don't have pi, though? You got 2 radians. You got 2 ways to do it. I told you, one of the very first things I told you was 1 radian equals how many degrees? 57.5 degrees. So I could take 2 and I could multiply it by 57.3 degrees, and it's going to be 114.6 degrees. That's one way. If you don't see a pi, you know each radian is 57.3 degrees, just multiply it by how many radians you have. There's another way to do it, though. You could reverse what we did on the last slide. You remember on the last slide here, we did pi over 180, right? You could reverse that and do 2 times 180 over pi. You do that, you're going to get 360 divided by pi, which comes out to be 114.59. What do you think about the two answers? They're the same, because you would round this to 0.6 also, so they're the same answer. So you could solve it either direction, either way you like. If you don't see a pi in the problem, you could just simply multiply it by 57.3 degrees, because that's what each radian is. Or you could multiply it by 180 over pi, because that's my conversion factor. So either way works. If you are going, well, in this case, we're converting from radians to degrees. So we're going to try to find out what the degrees are. When we want to get, when we had a pi in the problem, that's when you would substitute it. If there's no pi in the problem, you're not substituting it, you're just multiplying by it. So there was nothing to substitute at the beginning. So 3.5 would be 3.5 times 57.3 degrees, or you could put 3.5 times 180 over pi. Either way, you'll get the same answer of 200.55. This answer was actually 200.54. Which answer do you think is more accurate? Second one. Because 57.3 is rounded off. We had it, really, it's like 57.29 and a bunch of numbers, right? So 57.3 is a little bit rounded. When we use pi, we're using a more accurate answer. So using this pi right there makes it a little more accurate. So 200.54 is actually a little closer than 200.55. So that's going from the radian measure to the degree measure. So when you get to your homework, you should be able to convert either way now. So from radians to degrees or degrees to radians, back and forth. That would be that one. All right, we got a couple of slides left. We want to talk about degrees, minutes, and seconds. Now, picture 1 degree in your head. How big is 1 degree? It's pretty small, right? You think about a whole circle with 360 of them, and you picture 1 degree. Now, in your mind, picture that 1 degree broken up into 60 pieces. How small is that? Tiny, really small. Okay, that would be, those are called minutes. I know their time is minutes, but we're also going to break degrees up into minutes. So minutes has 2 meanings. It could be time, or it could mean little pieces of a degree. Now, so you took the 1 degree and you broke it up into 60 pieces, right? Now you take one of those teeny pieces and break it up 60 times. That's so microscopic you wouldn't even be able to see it, right? Those are seconds. Each minute is broken up into 60 seconds in time and in degrees. Those are important because if you're an airplane and you're off by 1 second or 2 seconds of direction and you go that way for 1,000 miles, then guess how far off you're going to be when you get there? Very far. Okay, so you want to make sure your minutes and seconds are very accurate so you can get right to the place that you need to go. So that's why these are important. That's why they do that. So breaking a degree into minutes, there's 60 minutes in 1 degree, and there's 60 seconds in 1 minute, so that means there's 3,600 seconds in 1 degree. 60 times 60 was 3,600. So let's see how we can convert 0.45 degrees into, 0.45 degrees into minutes. How did I get from 0.45 to this 27 minutes is what we want to know. Well, what does 0.45 really mean as a decimal? 45 out of 100, 45 hundredths. So let's put that down. This is 45 hundredths. I want to know what that would be if it was out of 60. Because degrees or minutes is out of 60. 60 minutes is 1 degree. So if I've got 45 out of 100, how much would that be out of 60 is what I want to know. So I'm going to take my cross multiplying and get 100x equals 45 times 60 is 2700. Divide by 100 on both sides, and you get x equals 27 minutes. That's how you got that answer right there. You took the decimal and figured out what it would be out of 60. So that is the first one. Now, let's go the other direction. How did I get from this answer to this answer? How did I get from 245 degrees and 10 minutes to 245.167 degrees? I see where the 245 is, but where did this 10 become a 1 or 0.167? How do I do that? How do I convert the 10 into a 0.167? What did I do to get from here to here? What does this 10 represent? 10 out of what? 10 out of 60, because then there's 60 minutes in 1 degree. So if I take 10 and divide it by 60, guess what comes out on your calculator? 0.167. You get that right there. So all you have to do is take your minutes divided by 60 and you'll get your decimal. All right, let's practice a couple of them. I'm going to move it up a little bit. Hopefully you have those done. I'm going to change, oops, my bad. I'm going to change this one. So erase that one on your paper. I'm going to change it to 34.56 degrees. And we want to convert that to minutes and seconds. Okay, so what's 0.56? What is this as a fraction? 56 hundredths. I want to know what that's going to be out of 60. What is 56 hundredths going to be out of 60? Okay, so let's get 100x equals, and then 56 times 60 is 800. Oh wait, hold on, it's not. So let's 56 times 60 is 3,360. And we're going to divide by 100. So you're going to get x equals 33.6. So what does that 33.6 represent? That's 33 minutes. But 0.6, I want to change it to seconds. Does that mean it's 6 seconds? No. What does this 0.6 represent? This right here represents 6/10. And I want to know what that would be out of 60 minutes, or out of 60 seconds, or out of 60 minutes here. How much would that be? So let's do our 10x equals 360, divide by 10, and x is going to be 36 seconds. So I've got 34 degrees, I've got 33 as my minutes, and I've got 36 as my seconds. So 34 degrees, 33 minutes, 36 seconds is the same thing as this right here. So think about what half of a degree is. Like what's half an hour in minutes? 30 minutes. So half a degree, this is a little more than a half, isn't it? Isn't 33 a little more than a half? Yeah, 30 minutes would be a half. So 33 is a little more than a half. So it's 33 minutes and 36 seconds is what that 0.56 represents. What about this one? This one's easier. To go from minutes and seconds to decimal is much easier. I'm just going to divide this by 60 because there's 60 minutes in every degree. And I'm going to divide this one by 3600 because there's 3600 seconds in every degree. This right here is going to give me 0.25. This right here is going to give me 0.003. So what do you think my decimal is? 125 point what? What do I get when I put this 0.25 together with this 0.003? 0.253. So that would be your decimal. If you've got this, your decimal is right there. Yeah. You're changing the degrees, minutes, and seconds to a decimal degree. This is still a degrees right there. It's just we took the minutes and seconds out and made it a decimal. So I just wanted to show you that you can go back and forth either way. All right, last couple of slides are more of what we're going to get in our little word problems, but they're not really tough ones because they're giving you the formulas already. So we're going to talk about arc length using radians. A circle has a radius of 4 inches. So this is 4 inches right there. You see that 4 inches? Find the length of the arc intercepted by a central angle of 240 degrees. Now I did show you how to do this in geometry. I don't know if you remember this little proportion, but we used it in geometry. We said that the part that we're looking for was the part of the circle. I don't know what that is. That's what I'm trying to figure out. The part of the degrees was 240. The part of the wait, hold on. No, it's not 240. The part is 240, but the parts go on top. 360 goes on the bottom, because that's my whole degrees. This is the part of the degrees, this is the whole degrees. This one right here would be your entire circumference. So the whole arc would be 2 times pi times 4. So my 2 times pi, 2 pi r is my circumference. So could I reduce 240 and 360 to make it easier for me? Yeah, I could first divide them by 10 and get rid of that. Could I reduce 12 over 36? Yes, divide them by 12, right, and get a 2 and a 3. So let's multiply 3 times x, get 3x. 2 times 4 is 8. 8 times 2 is 16, and we have a pi. Let's divide by 3. So we're going to get x equals 16 pi over 3. If I multiplied it out and then divided by 3, I'm going to get 16.76 inches. So if I start from here and go all the way over to here, it's going to be 16.76 inches around. Now that had a lot of work into it. We had to get the proportion, we had to cross multiply, we had to reduce, and we had to solve it. There is a shorter way to figure it out, if you know the radians. Because this S right here stands for arc length. This R stands for the radius, which I already showed you right here, and the theta stands for radians. Now, is my theta in radians right now? No, it's actually in degrees. So you could actually convert 240 to radians, but 240 is on your unit circle. You actually could look at your unit circle and see exactly what 240 degrees would be as a radian. How much is 240 degrees as a radian? 4 pi over 3 radians. Now remember, this is 4 pi over 3 radians to get to here. How long is each radian? How long is each radius? 4 inches. So each radian is 4 inches. So if I know that I've got 4 pi over 3 radians, and each one of them is 4 inches long, couldn't I just multiply those two together to get how long the arc is? Each radius is 4 inches, and you got 4 pi over 3 of them. What's 4 times 4 pi? 16 pi over 3. Does this look familiar? It was right there. You got the same answer either way, but you just multiply two things over here to get your answer. Now you may have to convert the 242 radians if you don't have it on your unit circle. You would simply take the 240 If you wanted to convert it to radians, you take 240, multiply it by pi, divide by 180, and reduce it, and you would end up with your 4 pi over 3 radians. So that you may have to do that if you don't have your angle in radians already. You might have to convert it to radians. And a lot of them are on your unit circle, so you could just get them from there. But that's a much quicker formula if you know the radius and you know how many radiuses there are. Just multiply them together and you'll have your arc length. It's a lot quicker. So that would be arc length. Now in your homework they're going to give you all the numbers you need. You're just going to multiply them. So it's going to be a lot easier for you on that. Okay, next one. Linear speed. Linear speed. How fast is the second hand going? Linear speed. So we've got a second hand of the clock. The second hand of the clock is going around the clock like this. Now we know it takes a minute to get there. It takes 1 minute to go around the clock. 60 seconds. But how far does it go in that 60 seconds? In other words, what's my circumference that it's traveling in that 60-second amount of time? How far is it going? We know it's going to be 10.2 centimeters long as my second hand. So I'm going to take my arc length, which I need it to go all the way around the circle. So I need it to do the circumference, which is 2 times pi times 10.3. That's my arc length. It's one time around the circle, circumference. My time is 60 seconds. That's how long it's taking to go one time around the clock. So if you were to multiply the top, you're going to get 64.088 over 60. 64.088 over 60. Yes. Yes, it should be 10.2. You're right. Sorry about that. 10.2. Yes, 10.2 centimeters long. So if you multiply all this together, you're going to get 64.088 centimeters. That's the whole circumference. And it's got to do that in 60 seconds. That means that it's traveling 1.068 centimeters every second. If it just went 1 centimeter every second, it would only go 60 centimeters, and that wouldn't be all the way around. All the way around from here, all the way around to here is 64.088 centimeters. So it's got to go a little bit more than 1 centimeter every second. Otherwise, it won't make it all the way around. So 64.088 is the complete circumference. Divided by 60 seconds, you're going to go this fast. 1.068 centimeters per second. That's how fast that second hand is actually traveling. If your second hand has a radius of 10.2. You can figure it out for whatever radius your second hand is. You can figure that out. Okay, moving on to angular speed. Angular speed. Let's take a look at the Ferris wheel. It has a 50-foot radius. That means it's 50 feet in one direction. It says it makes 1.5 revolutions per minute. Does that seem fast or not? So it starts here, it goes around one time, and then it goes another half. And that takes 1 minute to do that. So let's see how fast it actually is. Because we can apply that to our feet and yards and things like that. So let's see how fast that would actually be. First, you want to find the angular speed. What is the central angle in radians of 1.5 times around? What's 1 time around in radians? 2 pi. So what's 1 plus another half? 3 pi. Each half is a pi. So 3 pi over 60 seconds as long as it takes. It takes 60 seconds to do 3 pi, to do 1 time and a half. So if you were to multiply this and divide by 60, you get 0.157 radians per second. How much is 1 radian? 57.3 degrees. So this is a small amount of degrees per second. Probably like 1 or 2 or 3 degrees maybe per second. But that's a small amount of radians per second, so maybe it isn't going very fast. Let's convert it to something we might understand. Let's look at the linear speed. Okay, the arc length would be the length all the way around. So we want to take the arc length we learned on our last slide was the radius times the radians. So what's my radius of my Ferris wheel? 50 is my radius. What's the radian measure? I just learned it in the point A up here. What was the radian? It's right there, right? 3 pi. So 50 times 3 pi, and we're going to divide that by 60 minutes, or 60 seconds is what it takes to get there. If you were to multiply these two and divide by 60 on your calculator, you'll end up with 7.85 feet per second. 7.85, that's almost 8 feet. So if I look at the squares on the floor, I go 8 of those in a second's time, which would take me about a second. So is it going very fast? Not that fast. I could probably walk or kind of run that fast, right? So it's not going super fast because it's a Ferris wheel and they're not going to go really fast, right? Now, if you were to do that to your wheel on your car, look how fast that thing's going. That's going, depending on your speed, miles per hour, but it's moving. But this is a pretty small feet per second. So, I mean, that's not going super fast, but it's a Ferris wheel and it doesn't want to throw people off the Ferris wheel. Can't go too fast. All right, that was angular speed. The last one we have is the area of a sector. And again, we did learn this in geometry. You might have remembered it, you might not have, but we could use the formula part over whole equals part over whole, and that would also get me the area of a sector. That's the long way to do it, but if you have degrees like they do here, then this might be the smarter way to do it, because they already gave you degrees. If they gave you radians, let's say they gave you that was 2 pi over 3 radians, 2 pi over 3, which is exactly what it is in radians. You look at your unit circle, you'll see at 120, you'll see 2 pi over 3. If they gave you radians, it'd be smarter to use the formula. If they gave you degrees, it's probably smarter to use the proportion. Because the part is what I'm looking for. The whole area of the whole circle would be pi times radius squared. The part of the degrees is 120. A whole circle is 360. Could 120 over 360 be reduced? Yeah, to 1/3. So I'm going to get 3x, and we're going to get 70 squared is 4,900 times pi. 4,900 pi, dividing by 3. I'm going to leave it as 4,900 pi over 3. Now, we could convert that to a decimal if we needed to, but we're just going to leave it as 4,900 pi over 3. Now, let's look at this formula. If I knew the radians, all I have to do is plug in 1/2 times the radius squared times the radians, 2 pi over 3. Do you see anything I could cross cancel? The 2's. 2 and 2 cross cancel. What was 70 squared again? 4,900 times the pi divided by 3. We got the same answer both ways. Both directions we got the same answer. So you could use either one, but if they give you degrees, this is probably easier. If they give you radians, this is way easier. It just depends on, in the problem, what they give you. So to look at it, see what they give you in the problem, and then decide which formula to use. Yeah. Because remember, area formula is pi r squared? So pi r squared is our area formula. All right, so that's